The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so welcome to class today. Today I'm going to be talking about one of my favorite topics, enzymes and catalysis. And what I would like to do is give you an outline of where we're going today. First, we're going to define what a catalyst is. And we're going to focus on enzymes as catalysts. Then what we're going to do is describe the theory of catalysis. And we'll show how the theory can account for all experimental observations, or most experimental observations. We'll then talk about the mechanisms of catalysis. And we'll see that there are three basic mechanisms. I won't write them out now, but we'll come to them. And then, if time allows, we'll talk about another property of enzymes. These are all focused with amazing rates of reaction. And the second property of enzymes, besides the fact that they can accelerate reactions by 1 million to 1 billion fold, is their specificity. Okay, so that's where we're going. And what I'd like to do in the very beginning is show you why, spend a little time to show you why enzymes are important, okay? Why do you care about enzymes? That's why you care about enzymes. Look at this mess. That's what's going on inside your body. There are thousands of reactions going on inside your body. Without enzymes, no reaction. Okay, so you must care about enzymes. Okay, so, and what we're going to see over the course of the semester is that we can break down this mess into a few basic reactions. Okay, so here's Waldo. And over the course of the semester, as you've seen many times, we walk through central metabolism and all of the reactions. Now, a second thing about enzymes that I think sort of will be what you guys do for a living if you decide to become biochemists and enzymologists is, can we take our understanding of how these amazing catalysts work and design our own protein catalysts to do any reactions we want, not involved in the 10 or 12 basic reactions we have going on inside our body. And we can't do that now, but I would argue that understanding catalysis is a key requirement for getting to the point where we can actually do catalytic design. And the third thing that I think is really important is that 40 to 50% of all the drugs we presently use in treatment of antibacterial infections, the antiviral infections, the anti-cancer infections are all inhibitors of enzyme-based reactions, and understanding catalysis helps us to design better inhibitors. So understanding catalysis is central to many things that are important to all of us in society. Okay, so let me just tell you how I got excited about enzymes. So I went to graduate school, never had a biochemistry course. They didn't do anything about biochemistry at the molecular level. When I went to graduate school, I went to a lecture in the first year of graduate school, but it was given by a faculty member at Stanford, and he talked about an enzyme called linosterol cyclase that converts a linear molecule. Okay, so here's the linear molecule, but I have it folded up into 4 rings, and these 4 rings provide the basis for all steroids like estrogen and testosterone and cholesterol. And look at what this reaction does. One enzyme in a single step converts this linear molecule through a series of cascade transformations and hydride and methyl shifts into this molecule, putting in 6 asymmetric centers in a single step in 100% yield at 37 degrees and a pH 7. I said, my God, why do I want to be a chemist? You know, you sweat. There are no blocking hoops. You sweat to put in any kind of an asymmetric center. And here, this little protein has figured out how to do all of this under really mild conditions. And so this was a transformative experience for me. I remember the lecture clearly because I thought it was so amazing and had never seen that enzymes could catalyze reactions like this. So enzymes really are amazing. Okay, so what I want to do now is start by defining what a catalyst is. And a catalyst, it can be, for those of you who have had more chemistry, can be an inorganic ion, for example. It can be a small organic molecule. But for us, we're going to be focused on large macromolecules. And the macromolecules we'll see that we're going to focus on could be proteins or RNA, but most of the reactions found in our body are catalyzed by protein catalysts. And these catalysts increase the rate of the reaction without themselves being changed during the reaction. Okay. And furthermore, while they can increase the rate of the reaction, they don't affect the overall equilibrium of the reaction. They just increase the rate of approach to equilibrium. So they have no effect on equilibrium in solution, but increase the rate of approach to equilibrium. Okay, so what I want to do now is sort of define some of the basic properties of the catalysts that we'll be talking about for the next 15 minutes or so. So the first thing is that the catalysts we're going to be focused on are enzymes. Remember, we've spent the last few lectures talking about proteins. Enzymes are simply proteins, but then we'll see that they have special regions in the protein structure which allow them to accelerate rates of defined reactions. I also will mention that we have inside of us a machine called the ribosome, and the ribosome is the machine that makes proteins, makes polypeptide bonds. We're not going to talk about that in 507, but we talk about it in 508. And the amazing observation was made really initially by the seminal experiments by Harry Noller at UC Santa Cruz that you don't need any proteins to make peptide bonds. That was heresy at the time. In 2001, Stites won the Nobel Prize for the structure of the ribosome, and Harry didn't get the Nobel Prize. Bad. He's the one that made the seminal discovery, although the structure of a ribosome, which is, 2.3 megadaltons, is really sort of spectacular. I still get goosebumps when I think about that structure that was published in 2001. But Harry didn't get it. Anyhow, so that was a digression. So that took a few minutes off of my 50 minutes. Anyhow, and we're going to be focused on enzymes as catalysts. So why are enzymes important? They're important because, as I already told you, they accelerate the rates of reaction 10 to the 6, a million, to 10 to the 15th fold. Whoa, can you imagine that? Essigman always used to say to me, give him an example. That's like a lot. It's like faster than a speeding bullet. Do you know where that came from, faster than a speeding bullet? See, this is when I have a disconnection with my audience. Faster than, it's a bird, it's a plane, able to leap tall buildings at a single bound. Superman, Course 5, right? That's where our Course 5 logo came from. Okay, so let me just give you an example of this. And so this is taken from an article by Wolfenden. And this is the expanse of reactions that at rates that enzymes can catalyze that also can occur in solution. So if you take down at this end, the half-life of adding water to CO2 is 5 seconds. Okay, that's pretty fast. Okay, where do you see, why do you need water to hydrate CO2? Anybody got any ideas? Where have you seen that in the last few lectures? Hemoglobin. Why do you need that? Because in your tissues, all of the fatty acids and the glucose gets break down to CO2. The CO2, where does it come out? You exhale it. Somehow it has to be carried around and into your lungs from your tissues. And there's a key enzyme called carbonic anhydrase that accelerates even this very fast reaction by a millionfold. Okay? Let's look at another one that might be familiar to you. Let's think about peptide bond hydrolysis. We've just told you the ribosome makes peptides. What about peptide bond hydrolysis, which plays a major role in cell-mediated death, in blood coagulation, in controlling the levels of proteins inside the cell? If you look at the half-life of peptide bond hydrolysis, 450 years. That means if we needed this reaction in our lifetime, it would never happen. Okay, so if you actually look at the rate acceleration, proteases, which hydrolyze peptide bonds, have rate constants of about 50 per second. This rate constant is about 10 to the minus 9 per second. That's a rate acceleration of 10 to the 12th. So without these kinds of enzymes and many other kinds of enzymes, we would not be alive and we would not be able to function. So the description of rate accelerations is given by a term we're going to derive in the next lecture, Kcat over Km. A Kcat is a turnover number. It tells you how good your catalyst is in terms of per second. Km has a concentration dependence. So this is a second order rate constant, concentration inverse, time inverse. Okay, and this is what we use to think about how efficient enzymes are, as we'll see in the next lecture. So what I want to show you here is another graph that was made by Wolfenden, who's we were talking about data in the previous slide. And what I want to do is show you his comparison of enzyme-catalyzed reactions and non-enzyme catalyzed reactions. And we just heard with peptide bond hydrolysis, 450-fold rate acceleration. That's a lot. What do you notice immediately about enzyme catalyzed reactions? The Kcat over Km is on the order of 10 to the 6th to 10 to the 8th per molar per second. Does that ring a bell with anybody? Where have you seen a number like 10 to the 6th to 10 to the 8th per molar per second? What that is a diffusion constant of any two molecules finding each other in solution. So what is that telling us? That's telling us that inside the cell, enzymes have evolved to be so efficient that the rate-limiting steps are going to be finding each other in solution. It's physical. It has nothing to do with the chemistry. So you've had billions of years to figure out all this chemistry. And what limits everything, and we'll come back to this in a minute, is the the enzyme and the small molecule finding themselves. And so that's where this number of 10 to the 6th to 10 to the 8th per molar per second comes from. If you look at the non-enzymatic reactions, we just talked about hydration of CO2 versus enzyme-catalyzed reaction. What you see is they're all over the place. Okay, and so the staggering rate accelerations of 10 to the 6th to 10 to the 15th that you see are really based on the rates of the non-enzymatic reactions. And the enzymes have evolved, most of them have evolved over billions of years to be incredibly effective at what they do. Okay, so the other thing that I wanted to say about enzymes at this stage is that enzymes are usually, in addition to being great catalysts, they're also, you learn, I think, if you've seen enzymes before, that they're very specific for their substrates, which I'll call S, and we'll come back to this in a minute. So they only react, you have hundreds of metabolites inside of our body, they only will pick up and react with one of those metabolites. But in reality, I think what we found over the last 15 years or so is enzymes are not all that specific. They're specific for what they encounter inside us. So if you take them out as a biochemist and start messing around with them, they aren't anywhere near as specific. They don't have to be that specific because they never encounter these molecules inside the cell. So they're very specific for substrates in vivo. And in fact, many of them are promiscuous in vitro. And I think that's something that's been underappreciated. Okay, so this is number 3. I wanted to talk about specificity. Number 4, enzymes in general, if you looked at that metabolic chart, almost all those reactions can be subdivided into 10 to 12 reactions. And those 10 to 12 reactions, even though it looks like a jungle and a mess, are found in the lexicon that you have been given in the first lecture. So that lexicon provides a framework to think about all of primary metabolism. Now, in reality, there are many other kinds of reactions, but the ones that you're going to see in 507 can be limited to 10 to 12 reactions. So enzymes have a limited repertoire of reactions in primary metabolism. And so in this case, let me give a plug for the chemists. Chemists have the whole periodic table. Do we have a periodic table here? No. We're in the wrong department. We're in the wrong building. Anyhow, we have we have 50 elements where we can use to catalyze reactions. We can do all kinds of reactions catalytically, and we can do it with something small, like a proton, or something small like a metal with a little organic spinach hanging off of it. But what are we doing with enzymes? We have these big, huge molecules. So there's a playoff. Enzymes have a very limited repertoire of reactions they catalyze, while chemists actually can use are limited by their imagination to catalyze these reactions. However, as the world becomes more and more green, chemists are no longer allowed to use metals, for example, that can be toxic to people, and so people are rethinking and refocusing on developing green catalysts. So the question that you can ask yourself, is there any way that enzymes can enhance their repertoire of reactions that they can catalyze? And they can. They do that by using the vitamins on the vitamin bottle. So enzymes have a limited repertoire, but they increase this repertoire using vitamins. This is what we eat out of our vitamin bottle that are converted into cofactors. So the vitamins we eat have to be subtly modified and then get incorporated into the protein catalysts and greatly expand the repertoire. So many of you probably, how many of you take vitamins? Okay, everybody should be taking vitamins. Okay, why don't you take vitamins? Anyhow, So you can see you have vitamin B6, vitamin B2, vitamin B1, and over the next 3 weeks or so, we talk about the chemistry of how these vitamins interact with the protein catalyst to increase the repertoire of reactions to 10 that actual enzymes can catalyze. So, but in addition to the vitamins, I want to make mention of another type of catalyst. So most of the vitamins are organic molecules. One also needs to think about inorganic molecules. Okay, in inorganic molecules, copper, zinc, iron, all of those, if you look at your vitamin bottle, are at the bottom, and they're labeled inorganic. And they often, they almost always in introductory biochemistry courses get swept under the table. And in fact, many biologists don't think about metals at all. But 30 to 35% of all the enzymes have metals incorporated. And these metals are essential for the repertoire of reactions that enzymes can catalyze. So without going into any details, I just want to whet your appetites. Look at this guy. Okay, well, what are we looking at here? These yellow things are sulfurs. The purple thing is molybdenum, and the green things are iron. Okay, and in the middle of all these irons is this silver thing, which is a carbon bonded to 4 irons. Most of you probably aren't sophisticated enough yet to think that's amazing, but it was only 2 years ago that the X-ray crystallography, where we could look at things at atomic resolution, was good enough so we could see that guy. So what does this guy do? What's its function? Pretty damn important. It converts nitrogen into ammonia. So it turns out to be an 8-electron reduction, because not only do you produce ammonia, but 2 molecules of ammonia, but you also have to produce a molecule of hydrogen during that reaction. So this is the basic way we control nitrogen, one of the basic ways we control nitrogen in the environment. So chemists would love to understand how this spectacular inorganic molecule can mediate this, what turns out to be a 6-electron reduction. Another molecule, a cofactor molecule that's all metal-based that I think is equally amazing is this one. We have recently got an atomic resolution structure down to 1.5 angstroms. It has 4 manganeses and a calcium. Anybody have idea what this does? This is the cofactor that takes water in the presence of light, sunlight, and converts it into oxygen gas. Why is that important? Because we need oxygen gas to breathe. Okay, so anyhow, this one cofactor mediates that transformation. Pretty amazing. And that's a major focus of people who want to think about how these catalysts actually work, but we won't be discussing that further. Okay, we won't be discussing that further in 507. Okay, so I just wanted to point out here that, again, enzymes have a limited repertoire. Their repertoire is much less than what chemists can do, but they're amazingly efficient at what they do. So I would argue if we really could understand the basis of catalysis and how these things evolved to be able to do these amazing transformations, we might, if I was able to come back 50 years from now, see that we had designer proteins all over the place that could catalyze the specific reactions that we're interested in, not the ones that are found in our bodies. Okay, so the next thing I want to briefly mention is that enzymes, if you look at an enzyme, so it's a big macromolecule. We've looked at these in the last few lectures. The region where the chemistry or catalysis occurs is called the active site. And we've seen this before in the Tim-Barrel superfamily of proteins. And so there's a region of about 10 angstroms. We have your amino acid side chains that I asked you to try to remember and think about. We'll see those are key to making these rate accelerations so fantastic. This is where the chemistry happens. But I think it's now clear from studies that have been done in the last 15 years or so, this is not true. that one can make changes out here or out here. One can change the amino acids and totally turn off the enzyme or turn on the enzyme. So chemists use these small little molecules. Biology uses big, huge molecules. Everybody initially focused on this one little region where you can see the chemical transformation occurring. But what about the rest of the molecule? The rest of the molecule is also important. You cannot remove, in general, all of this spinach and come up with a catalyst that has these amazing rate accelerations. So the active site is very important, but so are specific amino acids outside the active site. And people have studied this because of technology of site-directed mutagenesis, which many of you have probably done in either 702 or in 335. Okay. So what implications does that have? And I just want to mention one more thing. I don't want to spend a lot of time on this, but our thinking about catalysis is changing dramatically and has changed and continues to change. I continue to study this, even to teach 507. Because it turns out, how does a change out here govern what's going on in this region where you think the chemistry happens? And it governs that chemistry because of conformational changes and movements. So another thing about enzymes that we need to do more thinking about, and this is a major focus of what people are thinking about now, is dynamics in enzyme catalyzed reactions. And so if you look at the time scale, and I made you think about size scale in the first few lectures, like how long is a hydrogen bond, how long is a carbon-nitrogen bond, a carbon-oxygen bond. You also need to think about time scales. And this is particularly true in the case of catalysis. What happens on the femtosecond time scale? That's pretty fast. That's a vibration of the bond. But what are you doing during an enzyme catalyzed reaction? You're breaking the bond and you're making the bond. So we'll see that the transition state of the reaction happens on the femtosecond time scale. Yet if you look at the criteria kcat, which is a turnover number of the enzyme, which is given in time inverse, they're usually on 10 per second to 1,000 per second. So we're on the millisecond to second time scale. So catalysis is happening way up here. Okay, now I've just told you that mutations outside the active site can affect catalysis. And so one also needs to think about the time scales in between these two extremes. I've also told you that an enzyme finding its substrate in solution can often be the slow step. So here you have nanosecond, microsecond time scales, and I'm not going to spend any time on this, but you can come back and look at this and think about, you've got all these side chains of your amino acids. You might have loops that are moving in and out and covering the active site. All of this dynamic interaction plays a key role in catalysis, making the enzyme as a whole important in the overall catalytic process. Okay, so that's my introduction to you for what an enzyme catalyst is. And so now what I want to do is look at the second bullet we were going to talk about, which I've already lost. Okay. We're going to how do we describe catalysis? How do we try to conceptualize in a theoretical framework all of the experimental observations that have been made for decades? And there are many things that are wrong with this theory, but this theory has stood the test of time, not only for biochemists, but for also chemists. And I think it helps us to think about how enzymes are able, with just the amino acid side chains for protein, to give us these amazing rate accelerations and specificity that we actually observe. So what we want is a theory to conceptualize catalysis, and this is transition state theory. And this is, many of you have seen this in some form before, either in freshman chemistry or maybe if you've had 560, people go through and derive all of the rate equations. What I'm going to do is just show you what this theory, a picture of how this theory helps us think about these catalytic transformations, and then how this picture helps us think more specifically about these amazing rate accelerations that we actually observe. Okay, so I can't remember what's on the next slide, but this is what a picture you often see when you're thinking about catalysis. So we have, this is chemical catalysis, but again, chemical catalysis, biological catalysis, really the same basic principles hold, that we have some substrates, A and B, going to products, and what's required. So, I mean, I think all of this is intuitive, but if you have two things coming together, they have to come together in exactly the right way to be able to make a bond. They have to remove all the solvent from outside them. They have to come together with enough force to be able to get over the barrier, whatever it is, to break one bond and to form a new bond. So that's true of all reactions, and everybody faces the same issues in terms of conversion of substrate into products. And the highest point along the reaction coordinate, so this is what we call a reaction coordinate diagram. And this is energy. So the highest point along the reaction coordinate diagram is called the transition state, TS. This is transition state theory. Okay, TS theory. And this is the point where you can never isolate it, because this is the point where all the chemistry is happening, the bonds are being made and broken. And the lifetime I just showed you on the previous slide is fast, femtoseconds. So you can never isolate a transition state. Everything needs to be aligned. That doesn't come free of charge. You have to do a lot of work to get to the stage where you can get this chemistry to happen. That's what our catalysts are doing. And then bang, the reaction is over at that time. So this is another way of describing the transition state of the reaction. And in reality, this is the cartoon you see in most introductory textbooks that are describing rates of reaction, but the reaction coordinate's much, much more complicated. And that's true in enzymatic reactions as well. So it's true of chemical reactions, it's true of enzymatic reactions. So you might have A plus B, and they might form 2 or 3 intermediates along the reaction pathway, okay, where you have many transition states along the reaction pathway. And each of these transition states would be non-isolable, but what about these little valleys? These little valleys are where you might have a chance to see an intermediate during the conversion of A plus B into P plus Q. So an intermediate, and if you're interested in studying catalysis and the chemistry of the reaction, you need to define what these intermediates are. They can be high or they could be lower in energy. They may be easy to isolate, non-easy to isolate, but they have all covalent bonds intact. So in contrast to the transition state where the bonds are being made and broken, you can never isolate this. You have a chance to be able, if you're clever and creative, which people that study mechanisms are, you can actually look at the intermediates along the reaction coordinate. Okay, so that's the reaction coordinate diagram. We're going to come back to these because I think they really help us to conceptualize how enzymes can go about achieving these fantastic rate accelerations. So from transition state theory, one assumes the following. I'm not going to go through the details of this at all, but the key point that one needs to think about in transition state theory is that, and this was first put forth by Linus Pauling. Who's Linus Pauling? He's like my hero. Okay, Linus Pauling, he's a vitamin C guy. He lost it when he got old. But in the early days, he's the one that could take a polypeptide chain, just a string of amino acids, and he sat there and he played with it. And lo and behold, he says, we're going to have alpha helices in proteins. How amazing is that? You've heard me talk about him before. He was the one that I think first conceptualized how an enzyme might catalyze a reaction. What do you want to do to catalyze a reaction? You want to lower this barrier. Okay, so how do you lower the barrier? You don't want the enzyme to bind the substrates tightly, and I'll come back to this in a minute. You want to bind the transition state tightly. So he put forth in the 1940s that the way enzymes might be able to catalyze their reactions is by uniquely and tightly binding the transition state of the reaction. And I think that turns out to be a really good way to conceptualize most enzymatic reactions. Now, transition state theory tells us, which again is not so appealing to me, but again, it works to describe most experimental data, that the ground state, so this would be the ground state, is in equilibrium with the transition state. So you might ask yourself, how the heck can you ever be in equilibrium with something with such a short half-life? Okay, so that's a good question to ask. But in fact, this framework, transition state theory, allows us to be able to explain almost all the experimental observations that we make as both chemists and biochemists. So this goes through and derives that equation, which I'm not going to do today. In the old days, I used to spend a lot of time deriving equations. Nowadays, I don't derive equations anymore. But the key equation that you need to think about is shown here. And the consequences of this equation are quite simple. It tells you that the rate constant for the reaction, so from transition state theory, the rate constant for the reaction okay, and where does this rate constant come from? A is going to some product P. You can measure it experimentally. So K observed is an experimentally measurable parameter, is equal to a bunch of constants called the transmission coefficient. This should be a kappa, Boltzmann's constant, temperature in degrees Kelvin, Planck's constant, times e to the minus delta G dagger over RT. Okay, so this is the equation. This is a constant. The transmission, this is Planck's constant, Boltzmann constant. This you can measure experimentally. Kappa is telling you, basically, the transmission coefficient is telling you the frequency that this transition state breaks down to form products versus going back to starting materials, and in general is on the order of 1 in most reactions. And so the key thing to remember from this equation, which explains the data and helps us to think about catalysis, is that as you increase the rate of the reaction, it's inversely related to the activation barrier. So what you want to do, this equation tells you, as you lower this barrier, the rate of your reaction becomes faster and faster. So the whole goal is then to figure out how to lower the barrier. If you can lower the barrier, this theory predicts that the rate of your reaction will be faster. Okay, so that's what we want to be able to do, that the rate constant is inversely related to the activation barrier. Okay, and so now let's look at an enzyme system specifically. So I'm going to draw the same kind of reaction coordinate that we've drawn over there for a chemical reaction. And I'm going to use a simple equation. The enzyme, E is the enzyme, S is the substrate, forms an enzyme-substrate complex. The substrate binds in the region that we call the active site over here. Somehow, the enzyme is able to convert itself into product. Okay, now most reactions are much more complicated than this. You have many substrates, you have many products. But it doesn't affect anything in terms of thinking about the problem. And then in the end, the product dissociates. Okay, so that's a simple reaction. You get something in there, your catalyst works on it, it gets converted to the desired product, and the product is released. Okay, so what I've told you now a couple of times is that enzymes have evolved to such an extent that often the physical steps and not the chemistry is rate limiting. So what are the physical steps? Here are the physical steps. Enzyme, finding substrate, and solution. That's a physical step. What is it limited by? It's limited by diffusion control. How fast can they find each other in solution? That's the number, 10 to the 8th per molar per second, that limits most enzyme-based reactions that I showed you several slides ago. What about this? We have product dissociation. What about product dissociation? That's a physical step too. You made the product sitting around, but in order for the enzyme to turn over again, to free up the active site, the product has to come off so it can bind another substrate. And here is the chemistry. That's what I care about. So, but what happens now is that if these steps are rate limiting, then you can't see the chemistry. So it's really challenging, often really challenging, to study the chemistry of a reaction because the rate limiting steps have nothing to do with the chemistry. So let me just draw a diagram. So you can draw a reaction coordinate diagram. And so what you have is some enzyme plus substrate, and it can form an enzyme substrate complex. You have a transition state of your reaction. The enzyme product complex can then dissociate to form enzyme plus product. So what you need to think about if you're thinking about how to accelerate the reaction is what is the bottleneck in the overall reaction. You don't want to start mucking around with something that doesn't control the rate of the reaction. So you need to know what the rate limiting step is in the reaction. And the rate limiting step is the highest barrier along the reaction coordinate. Okay, now I've already told you that this is a simple case. We have one substrate getting converted into product. Most enzymatic reactions are going to have many barriers. And so in order to affect the overall rate of the reaction, you need to figure out what's rate limiting. And somehow the enzyme has figured out how to lower the barrier to make this reaction easier to occur. Remember, I just told you that the rate constant is inversely related to this activation barrier. So if we can lower this barrier somehow, what we're going to see, if we can lower this barrier, now we have a lower overall rate of the reaction. So this theory allows us to think about what we need to do to make these catalysts actually work with rate constants of 10 to the 6th to 10 to the 15th times faster than non-catalyzed reactions. And I want to say one other thing before we move on. As with everything, I think it's good that we're in a field that's rapidly changing. Remember, I told you you have to think about dynamics. Okay, we no longer think about a single reaction barrier. That's in most of the textbooks now. Really, what we think about is we bring dynamics into this. I told you things outside the active site can modulate what's going on inside the active site. What we think about is a reaction landscape. And so one has many barriers that one has to get over. Almost all reactions involve multiple barriers, okay? So you got to figure out which one is rate limiting and lower that activation barrier. And enzymes, if you think about this, they're huge. Do they all fold exactly the same way? No. So we always think we have a homogeneous enzyme. No. If any of you work in UROPS, you'll find that out pretty fast. You use recombinant technology to fold things inside the cell. They don't all fold right. So you have all mixtures of things. And so you get a reaction landscape. And so this axis is bringing in the dynamics that I told you about earlier on that you need to think about, the conformational changes that occur every step along the reaction pathway. The enzyme is moving at all kinds of steps, reorienting everything to get the chemistry exactly right. Okay, so what I want to do now is, so that gives you a way to conceptualize rate accelerations. Now what I want to do is tell you what the major mechanisms are that the enzyme uses to enhance the rates of these reactions. How do we lower these energy barrier? Okay, so let me see. I need to start erasing somewhere. Okay, so we're on the third bullet over here. Mechanisms of catalysis. And what we're going to be talking about is multiple mechanisms of catalysis. We're going to be talking about binding energy, which is the one people have most trouble thinking about. We're going to be talking about general acid, general base catalysis, and we're going to be talking about covalent catalysis. And we will see that over the course of the rest of the semester, when we start talking about metabolic pathways, all of these mechanisms are used in almost all enzyme-catalyzed reactions to give us these tremendous rate accelerations. Okay, so what I want to do, that's the first time I did that. That wasn't too bad. Okay. Okay, so what are the mechanisms of catalysis? Okay, so how do we get 10 to the 6th to 10 to the 15th accelerations? Okay, and so the first thing, and I think the one that really is unique to enzyme catalysts compared to small inorganic or organic molecules, is the use of binding energy in catalysis. So this is the one, and this is also the one that's thought to contribute the greatest amount to these factors of up to 10 to the 15th. So binding energy in catalysis, and what does that mean? What do we need to think about? Okay, so the enzyme binds to its substrate. Okay, if we take this simple case, we need it to bind specifically. Okay, so that's a key part of the enzyme that we haven't gotten to yet, specificity. But what if it bound its substrate really tightly? Do you think that would be good? No. So it's not good, because what does it do? If it took all of the spinach hanging off of your substrate and made hydrogen bonds and van der Waals interactions, all the weak non-covalent interactions we spent a half a lecture talking about 4 or 5 lectures ago, what would happen is you would have tight binding. You would have lower energy. But what does that then do to the activation barrier? It increases the activation barrier. So the binding energy is the free energy released when enzyme combines with substrate, okay, but the key is that this binding energy is not used to bind completely, it's used for catalysis. So this energy is used both to bind substrate and this is the key thing, for catalysis. Okay. So what do we want to be able to do, and how does it do this? Okay, so if we look at this, if we look at our reaction coordinate diagram over here, we don't want to bind substrate tightly because this is the biggest barrier, the rate limiting step along the reaction pathway. What we want to do is lower this barrier. So how can we lower the barrier? We can lower the barrier by stabilizing the transition state. That now makes this barrier, probably can't read anything now, but that makes this barrier lower. How's another way you could lower the barrier? You could lower the barrier by straining the substrate to look more like the transition state. So you could strain the substrate in this form, and now, again, you would have a lower barrier compared to that barrier. So you're going to use this binding energy to stabilize the transition state. So, whoops. So we want to use binding energy to stabilize the transition state, to destabilize any of these or all of these could be true, destabilize the ground state, GS. Or what else do you need to do to get a reaction to work? If you have one or two substrates or even one substrate, your molecules in solution are all solvated. What you need to be able to do is get rid of the solvent. If you have two substrates, you have to bring them together. You have to bring them together at the right orientation. That doesn't come free of charge. You have to get the energy from somewhere, and the energy is proposed to come from this binding energy. So the binding energy is not used to completely bind the substrate, but to do all of these things to get your substrates ready to form product. So you can desolvate, and bring reactants together. You can freeze out rotational, translational entropy, so you're getting everything ready for the reaction to happen. So in this case, then, let me just erase this and make this so that this is clearer. What you can have now is so in the beginning, this is the barrier. If you stabilize the transition state, this becomes the barrier. If you destabilize the ground state, then this becomes the barrier. Okay, so what we're trying to do is lower this barrier to get the reaction to work. Okay, and so the major way that we do this is by using the interactions between the enzyme and the substrate, the weak non-covalent interactions between the enzyme and substrate, to help us do these things to enhance catalysis. Okay, so that's one of the major mechanisms of catalysis. A second, and this type of catalysis is unique to proteins. So the other two types of catalysis are used widely in organic or inorganic chemistry when you're designing your catalyst. I mean, when you're designing a catalyst, substrate binding, a small molecule, a big product release is still an issue. If you go and read the organometallic literature, people have trouble with product release all the time. So the issues in catalysis are exactly the same in biochemistry as they are in organic and inorganic. But now we have to deal with this big protein, which has these unique properties, one of which is that the whole protein is playing a key role in catalysis and allowing everything to align within tenths of angstroms to make these reactions work really efficiently, which chemists can't do yet. Okay, and I don't think we'll ever be able to design it, but we can evolve catalysts to become better and better so that they can do the same thing. That's the beauty of proteins, is that you can evolve them to become better and better catalysts. Okay, so the second mechanism, so the first mechanism is binding energy. The second mechanism, can't remember whether using I's or 2's. The second mechanism is general acid. General base catalysis. Now, as a chemist, what do you learn about catalyzing reactions? Well, one way you could do it is with a big fat proton. Protons are pretty good at helping you catalyze reactions if you go back and think about chemical transformations or hydroxide ions. Okay, what are the concentration of protons and hydroxide ions in aqueous solution at pH 7? 10 to the minus 7th molar. So you don't have much protons and hydroxide ions in the active site. So even though these are very good catalysts that organic chemists and inorganic chemists use all the time, they're using them in organic solvents. You can argue the active site of the enzyme is more like an organic solvent. But anyhow, this type of catalysis is called specific. So when you see specific acid or base catalysis, where does the general acid and base catalysis come from? It comes from the side chain of your amino acids. So remember the second or third lecture I said, oh, here are all the amino acids. Here are all the side chains. You really should know all of your amino acids. It's the basic vocabulary of all of biochemistry and the pKa's of all the side chains. Why? That's why. Because you can't understand anything about catalysis without knowing what these side chains of the enzymes are actually doing. So the general acid and base catalysis come from the side chains of your amino acids. So, what side chains do you have? Now you can have carboxylates. Anybody know what the pKa of a carboxylate is? Hey, Bogdan, what is it? Huh?
4 to 5.
Good. 4 to 5. See, he remembers. Okay. You could have imidazole. Okay. This has a pKa at neutral pH. Anyhow, you need to go back and look at what the groups are that can be involved in catalysis. And chemists for decades have studied how you can use general acid and base catalysis to give you rate enhancements. Now, what I haven't told you is the amount of rate enhancement. And so people over the years have measured that with binding energy, you can get factors of 10 to the 8th. If you look at general acid base catalysis from all the organic and inorganic reactions people have studied for decades, you get factors of 100 to 1,000-fold. Okay, now we need to get to a factor of 10 to the 15th in some cases. We've already gotten to the factor of 10 to the 6th. So obviously you're going to have to use multiple combinations of these mechanisms to give you these tremendous rate accelerations. Okay, so, and you will see over the course of the rest of the semester many active sites of enzymes with many amino acid side chains that are playing roles in general acid and base catalysis. And the last type of catalysis is covalent catalysis. And again, covalent catalysis means that you form, and where have you already seen covalent catalysis? You've already seen this when we talked about how do you study the structure, the primary structure of a protein. We use proteases with trypsin or chymotrypsin that can break down the big protein into small pieces. We went through the mechanism of that reaction. In the active site of that enzyme, there is a serine that forms a covalent bond. So over the course of the semester, you're going to see many examples, and so I'll just put in parentheses for those of you who don't remember. Go back and look at serine proteases. This is a classic example that's in every textbook. And how do we know how much rate acceleration you get from covalent catalysis versus not having covalent catalysis? We know this, again, because of organic chemists studying the detailed chemical mechanisms of these reactions. And we find out that in this case, we get rate accelerations of 100 to 1,000-fold. So what you see is that enzymes, and these are sort of the three general mechanisms by which all enzymes catalyze their reactions in some variation. Now, attributing out of this 10 to the 15th, 10 to the 8th is associated with this, and 10 squared is associated with that is extremely challenging. And there are a lot of people still trying to dissect reaction mechanisms out in detail. And I would argue that understanding how these different methods of work and synergize to give you these accelerations is the key to eventually designing new catalysts that can do what you want them to do that's distinct from biological transformations. Now, I think I'm probably over. I just want to say one more thing. I just want to give you a feeling for what you have to do if you're thinking about this reaction coordinate. What you need to do is think about how would you stabilize the transition state relative to the ground state. So what we're talking about is stabilization that's unique to the transition state and not the ground state. If you stabilize them both, what would happen? If you stabilize them both, so if we have okay, if you stabilize this guy and you stabilize this guy, the barrier would be exactly the same. So what you need is some way to uniquely stabilize the transition state over the ground state. So the question is, how much rate acceleration do you think you can get from a hydrogen bond? Does anybody have any idea? One hydrogen bond. So here you have a protein with 1,500 hydrogen bonds. But if you can get one hydrogen bond that's here in the transition state of the reaction, that's not over here, how much rate acceleration do you think you can get? Anybody got any idea? You can get almost 1,000-fold. So this, and you can do a very simple calculation. Can't remember whether I have this on the, okay, so that's it. Okay. So we can do a very simple calculation, and I'll use this to show you the calculation. Here we have our rate. This should be delta G. The dagger should be up in the air. So this is the enzymatic reaction. This is the iron equation. One has the same equation for non-enzymatic reactions. Okay, so here's the non-enzymatic reaction. In general, the non-enzymatic reaction can happen by a similar mechanism to the enzymatic reaction. Is just much, much slower. So if we assume, for example, that the rate difference between enzymatic and a non-enzymatic reaction is a factor of 10, okay, how much do you get, assuming that all of these terms are the same in the enzymatic and the non-enzymatic reaction? You can calculate a delta G dagger of 1.38 kilocalories per mole. For those of you who are modern, this is 5.8 kilojoules per mole. Sorry, I'm really old, so I still think in kilocalories per mole. But a hydrogen bond, one hydrogen bond is worth 2 to 7, compared to no hydrogen bond, is worth 2 to 7 kilocalories per mole. So a factor of 10 is 1.4 kilocalories per mole. So that shows you then that if you had 2 to 7 with one hydrogen bond, it can give you these factors of 1,000. So I think that's an observation that's something you need to keep in the back of your mind, because you think about it over and over again. It really doesn't take much to align everything in exactly the right way. And when I say hydrogen bond, these hydrogen bond strengths are really dependent on how everything is aligned. If they're exactly aligned, then you get much stronger bonds. They can even approach, in the gas phase, they can approach 30 kilocalories per mole. So having everything aligned, that's the job of this whole big protein, to actually give you catalysis. And I think I'm sort of at the end of my lecture now. I won't have time to talk about it. I went over already about the question of specificity, but let me just say, I think enzymes are really quite amazing. There's nothing like them. Faster than a speeding bullet. They can catalyze the rates 1 million to 10 to the 12th, 10 to the 15th fold. And they use really sort of the simple concepts that chemists have developed over the years, but the key to the enzyme is this big, huge molecule and the dynamics within this molecule that gets everything to align exactly right to be able to lower these barriers so that you convert your substrate into your product. Okay, guys, see you next time. The end.